Number 6. A team of 8 dogs pulls a sled with waxed wood runners on wet snow. Mush. The dogs have average masses of 19 kilograms, and the loaded sled with its rider has a mass of 210 kilograms. Letter A. Calculate the magnitude of the acceleration starting from rest if each dog exerts an average force of 185 newtons backward on the snow. Okay, so here we have a nice little Picasso. Here's the sled. Here's, I guess you can call it a dog. And what they told us that the sled weighs 210 kilograms. So let's put that in. 210 kilograms. They told us that the average mass of each dog, right, is 19 kilograms. So let's write the mass here of each dog is 19 kilograms. But, right, there's 8 of them. So let's just find the total mass because most likely that's what's important. 19 times 8. So we get 152. All right, so 152 kilograms would be the total mass of all the dogs. And what else do they tell us? They tell us then that each dog, right, applies a backward force where? On the snow. Okay, now we have to assume, because on this, you know, we're assuming that they didn't exceed their static frictional limit. They don't, you know, there is no paw on wet snow system here, so I have to make that assumption. So whatever force they're pushing back on the snow with is equal but opposite to the force that the snow is then exerting on each dog. Okay, so what that means is that if each dog, you know, exerts this force of 185 newtons, then that means the total force here for the dogs, I'll call it F of the dogs, is going to equal 185, again, multiplied by 8 because there are 8 of them. So we get 185 times 8, and we get 1480, right? So we have 1480, and that would be in newtons. That's the total force of all the dogs. All right. Now, let's see. Okay, so we got all that. So it says, all right, calculate the magnitude of the acceleration starting from rest. Now, it's a little, in my opinion, it's a little deceiving what letter A is asking. Let me state it a little differently. I believe they're trying to get at calculate the magnitude of the acceleration just at the start, meaning as soon as it just starts moving. All right, what's the acceleration just at the point of motion? All right, and no further than that. So if you think about how that's phrased now, we're basically looking for, right, we're basically thinking about the forces necessary to overcome static friction, right, not kinetic, because it's not really in motion, it's just about to get into motion, okay? So, all right, keep that in mind. Now what we need to do is create a free body diagram that details this situation, okay? So basically I have to look at this, well, here's the thing. The only thing that I'm calculating friction of is the sled in this problem. Okay, why not the dogs? Well, I mentioned that before. They don't give me paw on wet snow, you know, static or kinetic friction or whatever the case is, and I'm assuming that their paws grip the snow well and there is no slippage and stuff like that. Okay, so the only thing that's going to be producing any friction is going to be this sled, which remember has waxed wooden runners, and we are dealing with wet snow. So what's important here is first let's detail this picture, okay? So let's do a free body diagram of just the sled. So very quickly, we have 210 kilograms, so there's a weight, right? A component to this sled. It's pointing straight down, and the weight would be equal to its mass, 210 multiplied by gravity, which is 9.80. So let's just find the weight. So it's 210 times 9.8. So that's 2058. Considering sig figs, it should be 2060. Okay. Now, from this weight, right? Remember this this sled is resting on the snow. Well, you might say, well, it's getting ready to move. Yeah, no, I know, but it's moving in the x direction, right? It's resting in the y direction, we can say. There is no accelerations or velocities in the y direction. So, most importantly, accelerations. Okay, there are no accelerations in the y. Therefore, we do know what the normal force should be. Remember, it's just the perpendicular force that opposes, perpendicular force from the ground that opposes the weight. Okay, so here we have this vector pointing straight up, and the normal force here would be equal to the weight because it directly opposes it. All right, remember, you can think of this, sum of the forces in the y equals may. No acceleration, this whole side goes to 0. What are the sum of the forces? Well, I have this unknown, well, I know it, but let's just assume it was unknown normal force. I have a negative weight, so it'd be Fn minus 2060, and then I'd have to equal 0, and then I'd have to solve for this by adding it, right? So that's how I arrive at it, but we don't need to go through all that. Okay, now that I know the normal force, that enables me to do what now? It enables me to calculate the frictional force. And remember, frictional force will oppose the motion, so I'm assuming this thing is going to the right. So here's the force of friction, and specifically, since I'm trying to talk about it just as it starts moving, we're going to do static. All right, static friction. So how do we find that? Well, it says that the static frictional force is not equal to, is less than or equal to, has a maximum value of the coefficient of static friction multiplied by the normal force. So the force of static friction must be less than or equal to, now let's find the waxed wood runners on wet snow system in our table. Looks like it's right here, right? And the static frictional force, the coefficient of static friction is 0.14. So let's plug that in. So 0.14 and multiply that by now the normal force, which was 2060. And we get that the maximum static frictional force here should be 0.14 times 2060, 288, or 280, yeah, 288. So 200, and actually, well, 2 sig figs, right? So it should really be 290 newtons. Okay, so that's the static frictional force. So this is equal to 290, okay? Now, great. So we found then the frictional force on the sled. Now remember, that's the only frictional force in this entire problem. Okay, so now what I'm going to do is I'm going to back up and now I'm going to look at the entire system. Okay, so I'm going to draw now another set of coordinates, and you might say, well, why are we doing now the total system? Because remember, they're asking us calculate the magnitude of the acceleration. Well, of what? Acceleration of what? It doesn't state it explicitly, but I have to assume the acceleration of the whole thing, right? The whole system. All right, so here, let's plug in our force of friction pointing to the left. And we said that it was, I'm just going to call it F sub F, force of friction. That's 290. We have an applied force here to the right. Remember, that was the force that the snow is pushing on the dogs. It's equal but opposite to the force of the dogs pushing back on the snow. So we already found that to be 1480 newtons. Okay. And, that's it, right? I mean, we're only concerned about x components here because we're talking about acceleration, and the only accelerations are in the x direction since it's resting in the y direction on the ground. Okay. Now we can use our formula, right? We are looking for an acceleration. We should expect this to accelerate that way. Why? Well, because the right-handed force exceeds the left-handed force. So there is some acceleration to this. All right. So some of the forces in the x direction will equal the mass of the object being accelerated, or the mass of the system being accelerated, multiplied by the acceleration of that whole system. So some of the force in the x, we have a positive 1480 minus, because it's pointing in the opposite direction, 290, equals the mass of the thing that's accelerating. What did I say is accelerating? The whole thing, right? So the mass of the whole thing. So all the dogs and the sled. So we got 210 kilograms from the sled, and the total weight of all the dogs was 152. All right, multiplied by my A. All right, so divide this side by 210 plus 152. Divide this side by 210 plus 152, and we'll get our answer, right? The acceleration here is going to be 1480 minus 290. Take that answer and divide it by 210 plus 152. Careful with your parentheses. It looks like 3.3. All right, 3.3 meters per second squared. All right, that takes care of letter A. All right, so that is the acceleration just as it begins moving. It just has to overcome that static frictional force, okay? So now let's take a look at letter B. Letter B is now saying, what is the magnitude of the acceleration once the sled starts to move? So guess what? Doesn't this sound so similar to letter A? What's the only difference now? We're only talking about it in motion, right? So how's it going to change? It's only going to change by, instead of me using the static frictional force here, right? Excuse me, the coefficient of static friction. We're going to use the coefficient of kinetic friction. That's literally all it changes. So my calculation here, it's the same formula. I just, instead of 0.14, I use 0.1. All right, so let's do that. So let me, how do I want to do this? I'm going to do this in a small area because I basically did all the work already. I'm just going to do all the math over here, okay? So this is for letter B now. So we have the force now of kinetic friction, because it's a kinetic frictional problem, is equal to the coefficient of kinetic friction, which was 0.1, multiplied by the normal force. That hasn't changed, 2060. Okay, so the force of kinetic friction now is equal to 20.6. Now really, here's the thing, actually, excuse me, 206. Here's the thing though, this has one significant figure, so therefore this really has to be only one sig fig, so really should be 210, not even 210. It would actually be, no, it would be, yeah, it would be 200, right? It would be simply 200, okay? So, all right, so that takes care of that. That's a friction that's the kinetic friction, excuse me. And now all I need to do, remember, I took the friction before and used that as the friction for the whole system. So the only difference now is that the friction has gone down. So I'm literally going to use the same formula. I'm just going to change out the frictional value. So I have the sum of the, I'm using the sum of the forces in the x direction is equal to max. The 1480 is still the same. The dogs are still pushing just as hard on the snow. Minus now 200, the frictional force has gone down, equals the mass. Let's just do to 210. I'm just going to add them together now because I'm running out of space. So 210 plus 152. That works out to be 362. So 362 multiplied by AX. Okay, so just divide out the 362, divide out the 362, and now AX will be equal to, let's see, 1480 minus 200 over 362. So it looks like it's about 3.5, right? So 3.5 meters per second squared. Okay, so that's now the acceleration for part B. It should make sense, right? It should be larger than the initial acceleration because initially we had to overcome the coefficient of static friction, which is always larger. All right, now letter C. For both situations, oh no. For both situations, calculate the magnitude of the force in the coupling, all right, between the dogs and the sled. Okay, so just looking for where I want to do this. All right, so let me make a little space here and here. That looks great. And this is going to be for letter C. Okay, so in order to do this, I'm concerned. Go back to the picture over here, guys. I'm concerned with this coupling right here between the dogs and the sled. So there's a couple ways to look at this. A couple meaning specifically two. I'm not going to go through both, but I did detail both in the prior chapter's work. I don't remember the numbers, but you know, you can definitely find both methods there. I'm going to choose the faster one here. So I'm only going to look at it from the perspective of the sled. Okay, so let me draw a coordinate system, and I'm only concerned about the sled. So the sled has a weight, correct? So it has a weight. What's its weight? Well, that hasn't changed, right? We calculated it before. The sled's weight to be 2060 newtons. So the weight here is 2060, okay? The normal force is still the same, right? That hasn't changed either, all right? So the normal force here pointing up is still literally the same thing. It's still going to be 2060, okay? Now, for part, you know, it says for both situations, so let me go back to part A, right? The frictional force hasn't changed, okay? So the frictional force hasn't changed, so that is still what I calculate before, 290, right? If I look back to my picture right here, it's 290, okay? That hasn't changed, 290, all right? And now here's the thing. This part now represents the tension in the cable, or the tension in the coupling between the sled and the dogs. All right, you might be tempted to write in here, wait a minute, shouldn't this be the the 1480 that's over here? No, it shouldn't be, right? You got to read very carefully what it says in the problem here. It says, in letter A, it says, if each dog exerts an average force of 185 newtons backward on the snow. It doesn't say on the coupling. It talks about the force on the snow. Okay? So what that means is that we don't know what this tensional force is in the coupling. So I'm going to label that T. All right? Now, I didn't even really need to detail the Y forces. Okay? I kind of did, right, because I had to find the frictional force, and that depends on the normal force, but we already found it before. But remember, I'm only really concerned about the x directional components here. Okay. Also, now remember, what's the sled moving with? It's moving with an acceleration, correct? And what is the acceleration for part A? We found it to be 3.3 meters per second squared. So now guess what? We have everything we need, right? Now I can do sum of the forces in the x direction is equal to max. Sum of the forces in the x direction is the tension in the coupling. I don't know what it is. Minus, because it's pointing to the left, 290 is equal to the mass. Now what mass am I going to use in here? Well, remember, what system am I detailing specifically here? I'm specifically detailing only the sled. So that's why it's 210, okay? Times the acceleration, which we found before was 3.3. So simply add the 290 on over, right? Add the 290 on over, and we find that the tension will be in the coupling is 210 times 3.3 plus 290. So 383, and I think we got 2 sig figs here, right? So it should be something like, I don't know, 980 should be good. Okay, newtons. Notice how it is not the 1480. Okay, so that's great. That's for letter A. And then what do you think about how would we do it for letter B? It'd basically be the same thing, right? So I'll just put like a little A next to this. All right, now we'll do B. So here we go. What do we got? Where are we? Okay. So same forces, right? Meaning the weight has stayed the same, right? So the weight, the weight down here is the same. I'm not even going to detail it. The normal force up here is the same. That's fine, right? But now remember for letter B, they were specifically talking about kinetic friction now, right? So that was a little less. So we found that already. I don't have to detail it again. The kinetic frictional force was 200, all right? So 200 here. And now I want to find the tension in the cable. So now I'm looking for T, the same thing I just did, okay? So I literally use the same formula. Sum of the forces in the x direction is equal to the mass of the object in question multiplied that object's acceleration. So I have T minus 200 this time is equal to the mass. Remember, I'm only talking about the sled, so that's the 210 times the acceleration. Well, what's the acceleration for letter B? When we're dealing with kinetic friction, we found it to be 3.5, right? So that number changes, so 3.5. All right, so simply add the 200 on over, okay? Add the 200 on over to this side. I'm just running out of room, so I'm not going to write it. But the tension here will be equal to 210 times 3.5 plus 200. And it should be less, right? So we get 935 and 2 sig figs, so 940 newtons. All right? And that takes care of that. So, ladies and gentlemen, thank you so very much for tuning in. Really do appreciate it very much. Please do remember to subscribe. That would be great. And I will see you in the next lesson. Take care now.